Hello everyone, so lab 5 composition of concurrent forces. In this video, I'm going to represent a briefing about the theory behind this lab, and also I will talk in details about the procedure, the experimental procedure, and how to do the calculation to do this lab report. So you have another video, it's an experimental video. You need to watch the two videos. So the purpose in this lab or this experiment is to use a force table. So using the force table, we'll be able to find the experimental force, which balances two other forces. And this result will be checked using a theoretical method. So the component method or the analytical method and the graphical method. So you are going to have three different methods to find the equilibrium force. Now, before starting to explain the method and to talk about the force table, I present some basic knowledge to get you started. Let's start with the force definition and characteristics. So force may be defined as any action that tends to change the state of rest or the motion of a body to which it's applied. The force required, or we have like four quantities, characteristics to define or to describe a force or any vector. Okay, so the characteristics of a force are the magnitude, of course, in Newton, the direction, the nature, is it a pull, is it a push, and the point of application. So when two or more forces act on a body, they are called to form a system of force. And then the force meet at one point. Okay, so here a system of force, it's similar to what we did in lab, let's say in lab 4, we tried to find the net force. So here also are going to find the summation of force, but we have a system of forces that meet at one point here, the concurrent point in red. So we say we have concurrent forces. So C-O-N, the first part of this word means same. Current meeting. So the meeting point is the concurrent point. With forces meeting at a point, or they can emerge from the same point. Okay, so when we have a push, all the forces will meet at one point. When we have a pull, all the forces will emerge, will start from the same point. Now for force system, we have, let's say that we have two or more forces. So I'm explaining, or I'm taking the example only for two forces, because in the lab you will see that I'm going to use, I'm going to apply two forces and then find the third one. So when we have two or more forces acting on a point at the same time, the resultant force is a single force which is acting alone on this object, would have the same effect as the combined force. So if we take these two forces, F1 and F2 acting on this point, let's consider that this point is the point A. The summation or the resultant of these two forces, Fr, it has the same effect as F1 and F2 combined together. Okay, so that's what we mean by the resultant. How can we obtain the resultant? We need to construct a parallelogram using F1 and F2 as two sides of our parallelogram. So the diagonal of this parallelogram passing through the emerging point, let's say that this point we considered, it can be any point, so it's a point A. So this diagonal represents the resultant force Fr. Now, if the system or the force system acting on a body produces no external effect, the forces are said to be on balance, or the body experiences no change in motion. It's said to be in equilibrium. So here it's the definition simply of Newton's first law. We know that for Newton's second law that we have also studied in lab 4, sigma F net is equal to ma. So we are applying a force that will affect the motion. Okay, now Newton's first law states if the force system acting on the object produces no external effect. So if we add all the forces together, it's zero. What does it mean? It's zero. It means that A, the acceleration is zero. And when the acceleration is zero, we have two options. V is constant or V is zero. So when V is zero, it means that the system is at rest. When V is constant, it means that we have an object moving with a constant velocity. In this case, we say that our system is at the equilibrium. We are not applying any change to the motion, and the forces are balanced. So in other words, okay, if an object at rest, it will stay at rest. If an object is in motion, it will stay in motion at the same direction and same speed. Okay, so we are not changing anything with the state of our object. So at equilibrium, what does it mean? Balanced forces or equilibrium, or when we have, let's say, balanced vectors. In this case, the summation is zero. So F1 plus F2 plus F3 is zero. So based on this definition, we are going to be able to realize this experiment and to find the third force. So the two first forces will be given, and our target is to find F3, the balanced force. So by using three different methods. Now let's consider, let's think about our system. Let's consider that we have these three forces, F1, F2, and F3. The equilibrium, so to have this, we have an equilibrium. So F3 is the equilibrium force. So the equilibrium force is different than the resultant force. If you still remember here, we defined the resultant force, that is the summation of two forces. So the equilibrium force, F3, is different than the resultant force. It has the same magnitude, but opposite direction. So the resultant force is obtained by completing the parallelogram, while the balanced force, it has like an opposite effect. So F3, it has the same effect as F1 and F2 combined, while F3, it has the same magnitude, but in the opposite direction. That's why the equilibrium is equal in magnitude to the resultant, but it has an opposite direction because it balances the resultant. It will balance our system. So in this lab, as I have mentioned in the introduction, we will find the equilibrium force of the set of forces represented. You will see a table in your lab report. Okay, so we are going to use or to try three different methods. The experimental method using a force table. So this one will be explained in detail in the experimental video. The analytical method is based on the component method, and the graphical method is used on the tail-to-head method. So we are going to use two like theoretical or expected method to find the expected values. So by calculating or finding the component, or by measuring, for example, the length converted to the magnitude of a vector. So I will explain in detail what we are going to exactly do in this lab report. So we are going to find the third angle. Okay, as you can see here, it's a representation of the force table. Mainly we have F1. So F1, to apply a force here, we are going to add a hanging mass. Why it's a hanging mass? So we are applying a weight. Okay, we know the weight is equals to mg. So if we have a weight directed downward, so here we have a tension force. Okay, so we have an equilibrium. Let's say we have an equilibrium between the threads. Okay, so F2 is simply equals to the weight of M2. So M2 will be given. And here, as you can see, you have these graduations. So we'll be able to measure the angle. So theta 2 is also measured. Why do we need theta 2 or theta 1? Why do we need the angle? Because simply the force is a vector. And as you know, a vector, it has, as I have mentioned in the introduction, the force has a magnitude. So the magnitude of this force is m times g, where g is the gravitational, the gravity, and it has a direction, an x and y direction. So to know the direction, we need the angle to find the angle. Okay, so we will apply F1 and F2, and then you will see that by trial and error, we'll be able to record the mass and the angle required that should be suspended from the third pulley to have an equilibrium. Okay, so here it's F3. Our target is to find the magnitude, so the mass and the direction of F3. Now, regarding the analytical method or the component method, for this method, we need to use the vector definition and some trigonometrical function. So for this method, we need to know that a component of a vector is the projection of the vector. So here we have our vector in green. To find the projection of a vector along an axis, we draw the perpendicular. Okay, so here we draw the perpendicular lines from the two ends of the vector axis. Okay, so the perpendicular to the y-axis and the perpendicular to the x-axis. The projection of a vector on an x-axis, it's called its x component. And similarly, the projection of the y-axis is the y component. So here we'll be able to find Fy and Fx, or simply the x component of F, the y component of F. Now, how can we calculate the x component and the y component based on this angle or this representation? We need to use here the sine and the cosine method. We know that in a triangle, the sine is the opposite. Here it's the angle, so the sine is the opposite side over the hypotenuse. The cosine is the adjacent side over the hypotenuse. So if we check, f is the hypotenuse and fx is the adjacent side, fy is the opposite side. So that's why the x component is equals to f cosine theta, the y component is f sine theta. So here theta, you need to make sure that theta is a direction along the positive x. Okay, and also we can find the length and the direction from the component. So the length of the magnitude is the radical of fx squared, fy squared. The direction, tangent theta, is fy over fx. You know that tangent is opposite side over adjacent side, so fy over fx. In this case, theta is the inverse of the tangent of this ratio, fy over fx. So for analytical method, two forces are added together by adding the x and the y component. The components are added to get the components of the resultant force. So as you can see here, if we have F1 plus F2, it's equals to FR. FR, it's the resultant force. F3 is the balanced force. Okay, we cannot add all the components together. The X components are added together, the Y components are added together. And as you know, F, it had the same magnitude of FR, but opposite direction. So based on the analytical method, you are going to find first FR, and then from FR, you will conclude the direction and the magnitude of F3. So F3, it has the same magnitude. So its magnitude will be calculated from the X and Y component of R, the resultant. And it has opposite direction. So mainly what we are going to do, if this is the angle theta, the angle of FR is theta plus 180. Okay. Now let's consider here an example. Okay, you are going to use the same procedure to solve or to prepare your lab report. We have three forces. F3, our target is to find F3. So F1, it has a magnitude of 5 newtons and theta is 0. F2, it has a magnitude of 6.5 newtons and theta 2 is 110 degrees. F3, we need to find the magnitude and the direction. First, we find the X and Y component of F1. Here you can directly conclude that F1 is directed along the X direction because the angle is 0. So sine 0 is 0. That's why Fy is 0. So F1, it has only an X component. So if you want to write it as a vector, F1 is F1xi plus F1yj. It's 5i plus 0j, of course, in Newton. Now, same procedure for F2. F2 cosine theta 2 will obtain the X component. F2 sine theta 2 will obtain the Y component. So as you can see, what this minus means, it means that F2 is directed in the negative direction of X, but it's in the positive direction of Y. We write it as a vector. And here to find the resultant, so before finding F3, we need to add the X component together and then the Y component together. Because F1, F3, or F1 plus F2 is the resultant force, it's equal minus F3. So the X component of the resultant is the summation of X components of X of 1 and 3. So it's 2.8 newtons. Why it's 2 here? It should be a minus, not a plus, because it's 5 minus 2.2 simply. So it's 2.8. And Ry, it's 0 plus 6.1, it's 6.1 newton. So the magnitude is radical X component squared plus Y component squared, and the angle, the direction is tangent minus 1 Ry over Rx. So the direction of F3 is 65 degrees and the magnitude is 6.7. So regarding F3, so here it's for FR, for the resultant. So the resultant, as you can see, the resultant, the angle of the resultant should be between the angle of F1 and F2. Okay, because it's the diagonal. So if it's F1 and this one is F2, so normally the resultant is somewhere here. So that's why we have an angle between 0 and 110. Now to obtain the angle of the third force, the equilibrium force, we add a 180. So the angle of F3, it's 245 degrees. And the magnitude, it has the same magnitude. So F3, the magnitude of F3 is 6.7 newtons. And the angle, it's 245 degrees. So here it's an example. So here what you are going to do for the set of the values obtained or reported in your lab report. Okay, so this value of F3 will be compared to the experimental one. You will see that, for example, for the same set, I have recorded or experimentally obtained like a shifted value. The magnitude of F3 is a bit different, the angle is different. Now, regarding the graphical method, okay, so also we have two forces, they are added together. So here we need to draw them on a graph paper, okay, using a ruler and a protractor. So I'm going to take the same example. Of course, you need to set a scale. So here my scale is for each 1 Newton is represented by 1 centimeter. You can pick another scale. Okay, so the same example. So if F1 is 5 Newtons, if I want to draw it, and the direction is, or theta is 0, so it's directed along the x direction. So here it's F1, 5 centimeters using the ruler. Now for F2, we have the magnitude and we have the direction. We start by the angle. It's 110 degrees. So if you check here on the scale, here it's the 110. So first you put a point. Then using the ruler, you draw this 6.5 centimeters. So here it's F2. Now we will complete our parallelogram. Okay, or for the graphical method, we are going to use the head to tail method. Okay, so we are going like to shift F2 to the head of F1. Okay, so from the head of F1, we are going to like draw a symmetrical vector of F2. It's called F2 prime. So the resultant force in this case will be drawn from the tail of F1 to the head of F2 prime. Okay. So using a ruler, now we are going to use an opposite direction. So using the ruler, are going to measure the length of this line. So the distance between the tail of F1 and the head of F2 prime. So it's around 6.6 centimeters. So it's 6.6 newtons. And using a protractor, you are going to measure the angle. So the angle of this vector is 65 degrees. So again, it's the resultant vector. Our target is to find the equilibrium vector. So we draw a line with the same length, but in the opposite direction. And then you add a 180 to your vector, and you will obtain the value or the angle of F3. So mainly that's what you are going to do in lab 5. Okay, I'm going to send a data sheet. So in this data sheet, you have a table with the mass and the angle of F1, the mass and the angle of F2, and the mass of the angle of F3. So the first table is the graphical. Okay, so here's your lab report. Okay, so for the experimental method, I'm going to like to send you the values of M3 and the angle. So you need to calculate F3. Okay, these values are given. Okay, M3 and the angle 3, they are measured from the force table. Now, in the theoretical method, first part, you are going to use the component method. So you are going to calculate the magnitude of F1 and F2 and use the same procedure used in the slide to obtain F3 and the angle. Okay, and you need, of course, to show your calculation. For the graphical method, it's similar to what we did, what I did here. So you need to draw a graph, and to find the resultant. From the resultant, you will find the equilibrium force. Now, how do the theoretical values of the magnitude and direction of the equilibrium compare to the actual magnitude and direction? So here you need like to find the percentage error for both methods. So you compare what you find in the graphical method of F3, let's say F3 graphical, to F3 experimental, and also F3 component method to F3 experimental. So the experimental method, it's the one given in the data sheet, and the component method, the graphical method, are both F3. In this case, is the expected or the theoretical value. Okay. So comment on the possible sources of error. You need to list at least 3 sources of error directly related to the experiment. So please watch the experimental video and think about the sources of error affecting your results.